All right. I told you you didn't want to know, and it turns out you really don't. But I went while you guys were, during the break, and I asked the question, what would have happened if instead of after the Michael edition, if we had done the intramolecular aldol not using orange alpha proton 2, but instead using purple alpha proton 2. And please, this is all, I should not be recording, I guess. This is off the record. Don't worry about it. It is just fine for you to memorize that you take the other alpha proton from the alpha beta unsaturated carbonyl compound and you use that in your to make your enolate for your intramolecular aldol reaction. Some of you may wish to know why the other thing doesn't happen. The answer is it leads to a less stable product. So I drew what the products would be from there. You remove the proton from that other alpha carbon. It generates also a 6-membered ring, but one that is part of a bridged bicyclic system. You have one 6-membered ring in red, another in blue, all housed within the same larger orange 8-membered ring. I told you didn't want to know, but you insisted. Actually, none of you insisted. I don't know what we're doing here. The product, you brought this on yourself. The product looks like this, and or more accurately like this. There are problems actually doing the dehydration reaction. The geometry does not work very well to remove this proton and kick off this OH group. If you built a model, you would actually see that this carbon-hydrogen bond is not aligned with the ketone, such that if you removed the carbon-hydrogen bond, the negative charge wouldn't be conjugated with that ketone, not stabilized by resonance. And in any case, the ring strain really doesn't work out very well to have a pi bond in this position. We call this carbon that's part of multiple bridged ring systems the bridgehead carbon, and there's a rule in OChem about not having double bonds at bridgehead carbons. They're not very stable. Want to know more about that? You can take my chemistry class 552 in the fall. This is a great advertisement for that, I know. In any case, the answer for most of your what if and why doesn't questions about the Robinson annulation is the alternatives don't lead to more stable products. All right? So feel free to jettison and forget all of that. I'm going to put that somewhere where we don't have to look at it anymore. And right. So any follow-up questions on the mechanism for the Robinson annulation? All right, let's do some thinking backwards ones. What were the starting materials? And for the Robinson annulation products. Let's see. Okay, there you go. You can make that via a Robinson annulation. Skill number 1 that we're working on is what to pay attention to and what to ignore. So remember that a Robinson annulation product is a cyclohexenone. So your first step is to look at that, identify the cyclohexenone, and ignore whatever else you can. So have you got it? Is it this? No, silly Mr. Noodle, it's not. Mr. Noodle. I used to could do an Elmo voice, but as my age has, as I've gotten older, it doesn't work so much anymore. Nope, I just don't have the range. I was going to do an Elmo laugh. I lack the range, so. Nope, still no. Nope, haven't got it. Among my many impressions, that's no longer one of them. Okay, there is the cyclohexenone. All right, so as you get good at this, you will be able to look at this and say that one and that one. But at this point, it might be useful for you to go back incrementally. The immediate precursor. Oh, and by the way, at this point, having identified the cyclohexenone, you are totally free to redraw this with R groups. One of the great things about functional groups and molecular orbitals in OChem is that they help you identify the business end of the molecule, and having done that, you can often ignore everything else. So if you prefer R to methyl, that's fine. I don't really think that saves you any time, so I'm just going to leave the methyl group there. But we can use R groups here. Okay, they're not going to, everything else isn't going to participate in the reaction. You can abbreviate it and draw it in later if you want. You will get ultimately, so you don't need to abbreviate the R groups. Your brain will sort of just fuzz out stuff that's not important. But along the way, it can be useful to do that. Besides, I know you, and I know you're somewhat paranoid that your brain's going to fuzz out stuff you think is not important, but actually is important. So anyway, let's think of the immediate precursor. This is remember the final Robinson annulation is an intramolecular aldol product, which is an alpha-beta unsaturated carbonyl compound. So the immediate precursor to that should be the beta hydroxy carbonyl compound, right? Okay. And if this is a beta hydroxy carbonyl compound that's an aldol product, what is the bond that is made in an aldol reaction? It's that one, right? The one between alpha and beta carbons. At each stage, it may be useful to identify the bond that was made in that process. Okay, now let's think backwards one step. This is an aldol product. What would the starting material for the aldol reaction have been? You would have had an enolate on this alpha carbon, and the beta carbon should have been a carbonyl group. We won't worry about whether or not it's an aldehyde or a ketone. It's whatever this R group makes it. Okay? So that and then if you want, you can just erase the negative charge, or you can draw the neutral precursor to that intramolecular aldol reaction. Okay. So we've accounted for, in our final product, 2 bonds so far. All right, so that we've thought backwards from an intramolecular aldol product to the aldol starting material. Now, if you pay attention, you've got a 1, 2, 3, 4, 5 Michael product. A 1,5 dicarbonyl product. So your task now is to find where the alpha beta unsaturated carbonyl compound was and where the nucleophile was. And again, you might think, well, let's see, could this have been my Michael acceptor and this have been my Michael donor? And you might consider other alternatives. It's a good bet that this is the way it is, because remember, you've memorized that the thing that does the intramolecular aldol is the other alpha carbon of your Michael acceptor. So that's why I chose, thinking backwards, this portion of the molecule to be what's ultimately going to be my Michael acceptor, my alpha beta unsaturated carbonyl compound. If you forget that though, you might try the other way and say, well, what if this was my alpha beta unsaturated carbonyl compound? Oops, sorry, this. And this was my Michael donor. Is there a problem with that? What's the problem? My alpha carbon's already tertiary. Could I fit a double bond here? No, not without breaking carbon-carbon bonds. So this approach just doesn't work. All right? Okay, so then the immediate precursor to the Michael reaction is going to be the orange portion is going to have a pi bond between alpha and beta carbons. And then the purple portion is going to have been my enolate. Okay, already I'm done here on the left side. And then I just need to add the proton back there so that I get to some neutral starting material. And now, and only now, do I bother going back and filling in those R groups. Sorry, I'm getting confused. Is that right? Yeah. Okay. Yes? If that methyl group weren't there, would you know for sure how to break the Michael product into two pieces? You probably would have had a viable alternative there. Though, this gets back to something I said at the beginning of class. So rather than speak in hypotheticals, let's just go back to that example. There were two ways we could conceive of this Michael product coming from two different starting materials. From a synthesis point of view, breaking up something complicated into simpler things is better than breaking something complicated into something that's equally complicated. Synthesis works more efficiently when you take two simple starting materials, you put them together to generate one more complicated thing. That's called a convergent strategy. Going from here to the more complicated one, it's okay, but then you've got, in terms of synthesis, you've got, well, how do I make this? Whereas if I break it up into two smaller pieces, then, oh, I actually know where to get that. I can buy that. And so it's more of a strategy than in principle, it's a wrong thing to do thing. Yeah, go ahead.
If you go to the end product, how did you get that cycle?
Here?
Yeah.
Okay. Remember back here where I abbreviated stuff?
Yeah.
So I'm going to label the carbons that did not get sorry.
Oh, okay, yeah, sorry, I pulled it out. You
It's,
just draw the other,
right, sorry. So the only two carbons we've consistently drawn are those ones.
yeah.
This was an R group and that was an R group.
No, yeah, I thought you were saying that the yellow thing at the bottom turns into that one up above it.
Oh, no, no, no. No, sorry.
Those were the two parts,
Maybe,
You're good.
okay. Just to avoid confusion, maybe we'll,
So, yeah, it's the yellow one and the one below it are the two products.
two starting materials. Yeah, yeah, yeah. Okay.
Dr. Price?
Yes.
Wouldn't we also know that this is accurate because we have a beta keto, a di beta keto, a beta keto here as in the ring? That the H will then be removed from there because it's
Right. It just so happens if you look at the product, we ignored everything else all the way, but when we get back to what the starting material would have been, it makes sense that it looks like this because your alpha proton is actually alpha to 2 ketones. And so that's a very easy enolate to make. Right. Notice that the methyl group is probably there so that you can even do the intramolecular aldol product. If this had been a proton, maybe at that stage you're stuck because that'd be the most acidic proton. Okay, so let's review. If we look at that starting material, and I'm going to just draw it next to the products. Product starting material, thinking backwards, I'm all over the place, sorry. If we look at the Robinson annulation product and our starting material, and I'm going to label carbons. This is alpha and beta, and this is alpha 2 of my alpha beta unsaturated carbonyl compound. Those carbons end up there. Here's my carbonyl carbon and my alpha carbon of my Michael acceptor, no, our Michael donor, our nucleophile, our enolate, and those carbons end up here. All right. Everything else is an appendage. I'm trying to figure out a Joseph Smith quote we can modify to that, but okay, and those are the 3 bonds that we made. So I think your text actually recommends that when you see, when you're trying to solve a problem like this, and someone draws for you something like this, as an example, this is a second problem. Your text recommends that you redraw the molecule, putting the ketone and the double bond in the lower quadrant in the southern hemisphere with the ketone pointing to the left. And then sort of fill everything else in from that, which I'm struggling to do now, actually. Something like that. And at this stage, then, here is the alpha beta unsaturated carbonyl compound. Here is your Michael acceptor. These are the 2 bonds that you made. Sometimes it can help to label. This is your alpha, this is the alpha 1 and beta are where the double bond is going to go in your starting materials. And then this alpha 2 is the one that was the enolate in the intramolecular aldol. This is a carbonyl carbon, that's an alpha carbon. You break those into 2 separate pieces that look like this. And then this. I'm missing a carbon. Okay. All right. Questions?
So we're always going to assume that this set is the right set.
What set? Sorry, say that again.
Yeah, I should say that in order. The reactants that we created, there's the two different sets that can make it. In the last case, the other set.
Right. This
reasonable.
almost in the last case, trying to break apart your Michael product into two different things. There's going to be two ways to do that.
Right.
In general, this one's always going to make more sense. And if you're thoughtful about the questions they write, you're going to see them making choices that prevent you from doing the other thing. For example, we talked about how this methyl group there makes it so that the other choice isn't a good option. But this way, this strategy will always work to give you good starting materials for the Robinson annulation. Okay, so we've done like some of the problems at the end of the text. Encourage you to do some of the other ones until you're able to do it. I will tell you though that on the exam, likely I am not going to draw the cyclohexenone in this lovely arrangement that's most easy to see that you've practiced. That's annoying, I know, but don't worry about it. All you got to do is redraw the molecule in the nice, useful, and easy orientation that you're used to, and then you can go from there. Okay? Or just spin the paper around. Yeah, that's right. I ain't nobody's fool. Figure this out. No problem. Or you can actually get up from your desk in the testing center and walk around it, you know. Yep. Okay, what else? So, we're sort of, in terms of content coverage, we're sort of ahead of schedule. I think it's useful probably to do a little bit of practice. So what I kind of like to do is take some of the, there are some problems at the end of a chapter that I don't typically assign. And the reason for that is that they're really great at sort of testing your ability to deal with an unfamiliar situation and rely on what you know. But I feel like sometimes if I assign them as problems, students take them too literally, and they're like, well, how was I supposed to know that that was supposed to happen? And the answer is, you weren't. You were just supposed to play around with it until you figured it out. But that's unsatisfying sometimes because you want to know in advance what the right answer is and how you were supposed to know the right answer. Nevertheless, as a scientist, you often are given situations that are totally unfamiliar, and you have to rely on what you know to sort of figure out what might be going on. And so those skills are useful, and they're useful to practice because by the time you get to my exam, you're seeing probably, I mean, let's face it, even if I took a problem verbatim from the textbook, modified the words a little bit, rotated a few things, some of you would look at that and perceive that as an entirely different problem, right? So dealing with new and unfamiliar situations is an important life skill and is going to be useful to you on the exam. So I'm going to pick from the end of the chapter some sort of challenge problems. I do this and I'm sort of worried about it, but I think it could be a useful way to help out your mechanistic understanding. And some of these, I don't even know what the answers are. I mean, I haven't looked at the answers ahead of class, so we can figure these out together. All right? So, this is now in the realm of problem solving, not memorizing stuff. Okay, so are you ready for the horror? There's a 5-membered ring. Now, there's a lot of carbons here, so zigzag, zigzag. Whoa! Yes, thank you. You caught me. Texas carbon. Everything's bigger in Texas except for carbon, which still only makes 4 bonds, even in Texas. Darn it. So, you just need a strong base for this process to happen. And then the product that we get, this is just so terrible. I just can't wait to draw this for you. CO2 Ch18, by the way, if you haven't learned that yet, is just an abbreviation for that ester. Ooh, fun. That's not very pretty. Let's try that again. 7. But it's not actually that bad. I mean, it is that bad. So what do you do? And the question says, draw a stepwise mechanism. Thanks, that helps a lot. Hint, you need 2 Michael reactions. Oh, okay. I need 2 Michael reactions. That's interesting. So, in a problem like this, there is no prescribed way to approach it. You can approach it in different ways, and I'm going to just decide one way to start, but that may not be the best way to start. I find it can be useful to try to identify when the structure of a molecule changes this much, try to identify where the carbons in the starting material are ending up in the product. Seeing what connectivity has changed is often the key to figuring some stuff out. So, as a reference point, I see an ester group here and an ester group there. Okay, that didn't change. What else do I see? One important feature in this molecule that we noticed as I was drawing stuff is this quaternary carbon, the one that's attached to 4 different things. I don't like how I drew it. I happen to know that, and you may know this through intuition as well, we don't have a lot of reactions in OChem that generate quaternary carbons, that is an sp3 carbon that's attached to 4 different other carbons. And we certainly don't have a lot of reactions where we change a quaternary carbon to something else. So having seen a quaternary carbon, it's pretty reasonable to imagine that that's not going to change in the reaction. So I see a methyl group and then other stuff. And I've got a couple of choices for that quaternary carbon, don't I? I've got this one here, now attached to 4 different things, or I've got this one here. Now this quaternary carbon in purple is also attached to a long bunch of CH2 groups. So I'm pretty comfortable thinking that it's that one. Now, does that just make sense because I said it, or are you able to, or what do you think? Okay. That sounded arrogant. It wasn't meant to be. I'm sorry. Okay. So probably then, if that's the quaternary carbon and the esters there, probably this bit is the bridge between, is the connector or the linker between purple quaternary carbon and the ester group. Let's see if we've got actually enough carbons to do that. Let's start with the ester. 1, 2, 3, 4, 5, 6, 7, and 8. Did I draw that? Yep, okay, so 1, start with 8, 7, 6, 5, 4, 3, 2, 1. That seems okay. All right. So now let's see. I've got a methyl group here in blue. And if I'm going to let this purple one be 8, the quaternary carbon, then the only other methyl group I've got is here. And I also have a ketone, which I'm sorry, I apologize to red-green colorblind people. We are now exceeding my ability to use things, so we're just going to use green, and I'm sorry. Maybe we could use pink. I don't know. Sorry. We'll just use that. That's like the worst possible choice, but okay, there's our ketone. Yes?
In the product, is that a cyclohexane or a cyclopentane ring?
Where?
In our product with the carbonyl carbons attached to it.
Well, right. Are you noticing that you've got a 1, 2, 3, 4, 5, 6 membered ring? But there's also a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 membered ring here. So, and that can be useful. Now let's use, we're running out of colors, but we'll use gray. See if we can identify the 5 membered ring in the starting material and figure out where that is in the product. So here's the 5 membered ring in the starting material. Here's the 5 membered ring in the product. Okay. Having done that, we have now tracked down all of the bonds in the starting material that are still present, basically unchanged in the product. What's left? Ta-da! Are the 2 bonds we made. Okay? 8 and 7. Oh, right. That was there to begin with, which I suppose we could have, yeah. All right. Now, it may help us out to number the atoms of that 5-membered ring. So let's just, there's no right, there is a right way to number atoms of a ring, but nobody cares to know the rules, so we're just going to do whatever we want. Let's now look and number them here, 8, 9, 10, 11, 12. The bonds that we've made are between 3 and 9 and between 12 and 2. Now, look at our starting material. 3 is a beta carbon. And 9 is not a beta carbon, it's an alpha carbon. It's alpha to the green ketone. Enolate attacks beta carbon, Michael addition, Michael donor, Michael acceptor, okay? So we've just identified one of the two Michael reactions. This is a Michael donor. We're gonna make the enolate at alpha carbon 9, and we're gonna attack beta carbon 3. This is the Michael acceptor. Now, how about the bond between 12 and 2?
The negative charge created at 2 carbons has been attacked at 12 by.
Oh, okay, negative charge at 2 created by what?
So when you just go to pi bond.
Oh, so you're thinking, so it's true that over here on 12 is a beta carbon to the green ketone, right? So we're envisioning,
I was saying when you do the reaction with 9, that
okay,
relates to the beta carbon on 3.
right, so you're thinking sequence, right? Which one has to happen first? And the idea is I can't use, I can't make the enolate, to make the bond between 2 and 12, I would have to make the enolate here with red alpha and then attack green beta 12. But this proton is not acidic because it's held perpendicular to the pi system. It cannot align. There's no way to resonance stabilize the negative charge if this proton were removed. You can draw out the structure of the,
No, what I was trying
yeah,
to say.
so you say you got to do the other one first.
No, what I was saying is when you take off the proton off of 9,
Yes,
can you attack 3, and then once you do that,
yes.
it goes on. Okay.
Yes, right. So there's a reason, now that we've decided which bonds we're going to make, and we've got reasonable connectivity, it makes sense to do the remove proton, a green alpha proton 9 first, and have that be a nucleophile. Now we're going to do mechanism, because once I do that, alpha carbon of my enolate attacks and makes a bond with the beta carbon. That's horrific. We can draw that here, and that's a 1, 2, 3, 4, 5, 6, 7-membered ring. Gross. One, 2, 3, 4, 5, 6, 7. Okay, let's see, 7 is the beta carbon, alpha carbon, ester. Now that's negatively charged. Okay, now that does the conjugate addition okay, well, let's actually not draw it that way. After we do that, that makes the bond between 9 and 3. Sorry. I'm realizing how much the colors are helping. Oops. You are welcome to bring highlighters, colored pencils, whatnot to the exam. You can't erase very good. I guess colored pencils you could erase. Yeah. You can always bring scratch paper.
Bring your molecules.
Model set works too. So we've just made the new bond between 9 and 3, and now 2 has a negative charge on it. And look, having made that bond between 9 and 3, carbon 2 is already close to carbon 12 to do the intramolecular Michael, the second of 2 intramolecular Michael reactions. I mean, not easy, but once you identify the pieces, it is hard to draw these, but at least conceptually what's going on is just a Michael reaction. Okay. That was a challenge. Somebody, it sounded like Dwight was just saying, Michael! You can bring, what? Do you want me to build that for you? Sure. All right. Now, let's revisit this because I know that that's a stretch. What are you having a hard time seeing? It. Okay.
I'm kind of having a hard time seeing the bond between the 9 and the 3 at the very
Okay. Okay.
It's pretty easy to see now.
Well, yeah. You see alpha proton attacks alpha beta unsaturated carbonyl group. We could simplify this, and actually maybe it's useful to do. Use R groups. Forget for a moment that these are all tethered together. Put an R group here. I mean, the way that would look is this. Erase, 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 erase. Yeah. I think part of the challenge is you can get here, but how on earth were you supposed to know that doing that would generate this shape? And you're really not. In fact, I didn't either. I wouldn't have been able to predict that shape. I just took it from the product and tried to keep everything as close to the shape of the product as I could to help me see what was going on. All right, what else? All right, let's see if there's another equally bad one, shall we? I don't, oh, do we dare? I don't know if I dare. No, I don't.
Is it one that you want to leave last week?
Yeah. Okay, let's get started on one at least. This is the last one. This is actually 18.72. By the way, if you want, I mean, this was, the one we just did was 18.70. 18.72. This is like aversion therapy by just making you deal with things you hate. By the way, stuff like this is total synthetic organic chemistry flexing. Like, this is what they do at their meetings. They like to show big products, show massive changes in connectivity, and assume that you're following along. And you're supposed to sit there like, whoa, that guy's smart. And it's a little bit irritating. I like to be able to break it down to things that are simple, but to show that great complexity can arise from simple things. Here's this horrible starting material. Here is the product. Oops. Bridged, yep. Okay. This is a key step in the synthesis of an antibiotic called abyssamycin C, which was isolated from sediment collected almost 1,000 feet below the surface of the Sea of Japan. So where natural product chemists get their natural products is really another bizarre story. Add a base and a mild acid. That's helpful. Yeah. Yeah, I don't know that it does. I'm not. Okay. So I haven't looked at this. I'm not totally sure how to solve it. We've got the right connectivity. Let's start by identifying groups that are identical and not changed. Okay. So one that is not changed is there. Another that's not changed is there. Okay. Notice between those two groups that don't change, you have an epoxide, and so it looks to me like this OH, here used to be the epoxide, right? And that what we've done is an epoxide opening reaction. So I'm going to highlight that bond and just write a note to myself. I think we made that by opening of an epoxide. And actually the fact that relative to the ring those two groups are trans to each other is evidence that that was an epoxide opening, backside attack, right? Okay, well then let's see if we can figure out who did what. Huh. So I don't know where that oxygen came from. Let's label it in purple. Okay, do you notice that I no longer have an ester anywhere? Actually, I started with two esters, right? Yeah. One of those esters had, we're out of time. Oh, that's sad. So it's probably this one. All right, that may be enough to get started. So actually we'll work on that Monday. We're going to move on to benzene on Monday, but solving this problem, we're almost there. All right. Hello, everybody. Happy Friday, and we'll go ahead and dig in. We're going to review the Michael reaction, then we're going to introduce something with a fancy name that's not actually that fancy, called the Robinson annulation, and then we'll practice. Right, so the Michael reaction is a form of conjugate addition. That's where you add to the beta carbon of an alpha-beta unsaturated carbonyl compound. You've seen two examples of this kind of thing before we reviewed last time. One was cuprate addition to the beta carbon. The second was the reverse in the retroaldol. You have to have the OH minus attack the beta carbon first to give you the conjugate base of your beta hydroxy carbonyl compound. In terms of the Michael reaction, specifically that refers to an enolate adding to the beta carbon of an alpha beta unsaturated carbonyl compound. You can draw the intermediate that forms afterwards in one of two ways. The intermediate that forms afterwards is itself an enolate, which you can draw with the negative charge on the alpha carbon, or you can draw the resonance structure where the negative charge would be on the oxygen. Either of those resonance structures is just fine, though protonation on the alpha carbon is favorable because that gives you the more favorable keto product instead of the enol product. And then we talked about how the product of the Michael reaction basically gives you two carbonyls that are on atoms 1 and 5 respectively. So this enolate happens to be a beta diketone, but in any case, if you start counting with the carbonyl carbon of your alpha beta unsaturated compound, 1, 2, 3, 4, and 5, the carbonyl of your enolate is on carbon 5. And I suppose if a good structural pattern to look for something that is the product of a Michael reaction is this spacing of carbonyls. If you like Greek letters better than you like numbers, you can go gamma and delta, but I don't know that that actually helps you. So a delta carbonyl compound, yeah, that's actually worse, so we'll just go ahead and undo that. All right, so that's the Michael reaction. It can be useful to think backwards and ask what were the Michael products that led to what were the starting materials that led to the Michael product that might be given to you. So, as an example, let's do what were the starting materials, and this of course isn't going to be multiple choice, but you can imagine how you would format this in a multiple choice way. Okay, that's fun. What were the starting materials, and given that this is a Michael product? Okay, so how I recommend you begin is look for the structural pattern that characterizes all Michael products. Look for carbonyls, 5 atoms, spaced 1 and 5, a 1,5 dicarbonyl compound. So I don't have a lot of choices here. I've got this carbonyl here and this one there. I could start numbering here 1, 2, 3, 4, and 5, or I could number here 1, 2, 3, 4, and 5. Either way, I've got that spacing, so I know that both of those carbonyl groups are going to be involved. Now I sort of need to decide which portion of my molecule was the alpha beta unsaturated carbonyl compound and which portion was my enolate nucleophile. So to do that, just sort of pick one. Let's suppose, so we've identified our string of, let me just highlighted, I guess, in gray, our string of atoms in this sort of 5-atom chain that ends in carbonyls. What we don't know is whether, if you look at our Michael product over there, we don't know whether it should be split into either of the following ways. Was this the alpha beta unsaturated carbonyl compound and this was my nucleophile? Or alternatively, would it have been reasonable for it to be this way, this my alpha beta unsaturated carbonyl compound and this my nucleophile? What do you think? You like the first one? Why? You're not wrong, I just don't know, like, why do you like that one better? So, right, if this were the way we're gonna arrange it, this is the bond that we made, meaning that this would be your enolate, this would have been the alpha beta unsaturated carbonyl compound. Over here, it's a little trickier to see how that would have worked. Could we still do it? I don't know. I think, so let's now sort of ask ourselves, before we draw any conclusions, now that we've broken the 1,5-dicarbonyl compound into two sort of potential connectivities, if it's the one on the left, and this is the bond we make, and this is our nucleophile portion, and this is our alpha beta unsaturated carbonyl portion, then what's the immediate precursor? If I erase this bond, this used to be an enolate, and then what did this used to be? You got to have that there, right? So that becomes, that's our alpha beta unsaturated carbonyl compound, and here's our enolate. Okay. So I'm going to use like the retrosynthetic arrow. What if we do that here? Erase, whoops, I guess it's going to, everything goes, huh? This would have been my enolate, and this would have been, I'm sorry, that's my alarm in the morning, so suddenly I'm like, could have been that. Okay. Is there anything wrong with an intramolecular Michael reaction? Not really. In fact, I think the one on the right is kind of a creative solution. Now, if you want to take my Chemistry 552 class in the fall, nobody's ever done that. I mean, some people do take the class. I just think nobody that takes 352 with me has ever signed up for 552. I guess I'm a sufficient deterrent. But there are issues with to think about in terms of, can the negative charge on this carbon actually reach the LUMO on this portion of the molecule, whether the geometry works out nicely. There's a whole set of experiments in OChem relating to cyclization reactions called Baldwin's rules, and I think this one is allowed. You don't actually want to know this, but this would have been called a 5-exotrig cyclization, and I believe that's allowed by so-called Baldwin's rules. Anyway, it would just be a question as to whether the geometry works out very well or not. I'm not sure whether you would have preferred the cis or the trans isomer here. I don't necessarily want to worry about that. I think if you were planning a synthesis, this makes your job, in terms of retrosynthesis, going to two simpler molecules makes your job easier. going from a cyclic molecule to an equally complicated but not cyclic molecule is okay too. So there's, I don't really have a good preferred option for what the good Michael starting materials would have been. Either of these are okay. Any follow-up questions you want to ask about that?
So using 2' carbons versus 1' doesn't necessarily change the time.
So you're saying this is secondary versus primary.
Yeah.
For enolates, no. Right. Doing the attacking conjugate addition is different than conjugate addition is different from substitution chemistry. But no, I don't think there would be an advantage to having your negative charge on a primary versus a secondary carbon. Yep. Enolates are flat because they're conjugated, right? Sp2 hybridized all the way through here. Alpha beta unsaturated carbonyls are flat, so it's not like approaching an sp3 carbon where sterics are a major issue. These things sort of approach side to side, kind of like in a Diels-Alder reaction. So sterics aren't such a problem. Okay, let's do a predict products question with a Michael reaction. Some of these are kind of boring, but what are we going to do?
Make them interesting.
Yeah, I suppose we could color. I don't know. Coloring's a great idea. Let's see. I'll just choose one that has a 6-membered ring, which I know is threatening. But by the end of this class, you're going to view a 6-membered ring as a friend. All right. And we'll use a base. Now, we haven't seen this before. I will draw this molecule out. This is a beta dicyano compound, but it should look fairly similar to a beta dicarbonyl compound, right? As with the beta diketone, if you removed a proton here, you could delocalize the resulting negative charge by resonance into those cyano groups, all right? And we can look up the pKa. I forget what it is, but it's pretty low. It should be in the sort of 10 to 15 pKa region. So this is just another example of a beta dicarbonyl compound that the base can remove a proton to give you an enolate nucleophile. It's also clear that this has to be your enolate because here is your alpha beta unsaturated carbonyl compound. So even if you looked at this and you were unfamiliar, it has to be the enolate because the other thing is the other reactive partner, okay? I guess what I'm trying to do is help you know how to navigate unfamiliar situations because that's the number, I don't know, is that the number one problem on the exam other than, I think so, is looking at something unfamiliar and not knowing where to begin or where to start. Go ahead.
Does it always attack at the beta carbon?
Does the enolate always attack at the beta carbon? Clearly not, because we've done aldol reactions where the enolate attacks at the carbonyl carbon. So a question that I feel like doesn't have a satisfactory answer in this chapter is, how do you know whether it's going to do the Michael reaction or the aldol reaction? And you don't, and that's why the question says, draw the product formed from a Michael reaction. So, yeah, I think you sort of have to be told. Now, I don't know of any examples in the chapter where given a choice, when it's alpha beta unsaturated, that it attacks the carbonyl carbon instead of. So So I think it's a good bet with predict products questions if your nucleophile is an enolate and your electrophile is an alpha beta unsaturated carbonyl compound, doing the Michael reaction is the right thing to do. Now, in a mechanism question, that's a different deal, right? Because in a mechanism question, you have a starting material, you have a product, you just have to connect the dots. So in a mechanism question, do reasonable mechanistic steps to get you from one to the other. And you can use the product to tell you which way you're going to go. And we'll see some examples of that in a little bit. That's a good question. And I think the answer is if your electrophile's alpha beta unsaturated and your nucleophile's an enolate, do the Michael reaction. But yeah, in this question, that's deliberate. That's why they're saying what to do. Okay, others? All right, well, having identified the enolate, what's going to be the enolate, let's take ethoxide and remove a proton from this basically beta dicarbonyl compound. Any other questions about how I knew what to do there? Because I realize that's a new molecule we haven't dealt with before. If you forgot what CN is, then yeah, I can see that would have been pretty difficult. Do you see how that enolate is resonance stabilized with pi bonds? Yeah. Okay. So now what? Attack. And you can draw that mechanism in a couple of ways. You could simply show the electrons moving on to the alpha carbon. You could also show something like this. Either way gets you to a valid resonance structure for the intermediate. Here is the new bond I made. Here is an enolate intermediate. I'm going to protonate on the alpha carbon because the keto form is more stable than the enol form. And that's going to get me to this product. Oops, nope, there's no double bond there now. That's the bond that I made. Okay. Okay, so that's probably worth some practice just until you're familiar with it. I think it's probably easier in the forward direction than it is in the think backwards direction. It's probably pretty reasonable for me to write questions in either direction. So practice on that a little bit. All right. So now your favorite is going to be learning to make a six-membered ring that looks just like this. No, make it stop. So the section of your text that talks about this calls this the Robinson annulation. And Robinson is the person that discovered it. Annulation comes from the word for ring. I don't know if it's Latin or Greek, but annual, the year keeps coming around, or Spanish anillo for a ring, right? So we're making a ring. And it's a specific kind of ring. The kind of ring that's going to be made is a cyclohexene-one. So that is a Robinson annulation product. And I'll show you how this works. What's the best thing to do here? Sure, why not? Okay, so I will point out that one of the most challenging things about the Robinson annulation is that these are basically equilibrating conditions, very much like the aldol. So there are going to be places along the way where you are going to propose reasonable alternative side reactions, and you're going to ask why that doesn't happen. And I'm going to tell you it probably does, but this pathway leads to the most stable product. It is a ring, a 6-membered ring, which is a pretty stable product, and it's conjugated. In other words, the double bond of the ene is conjugated to the pi bond of the ketone. And both of those factors make the option that I'm going to show you more stable than the alternatives. So here is a simple starting material. And here is the other reactive partner. I am not worrying at this point about, well, if you've been practicing at the aldol reaction, you should be able to see how this on the right is actually the self-aldol product of this on the left. That being said, in the Robinson annulation, how have we chosen? This is going to be our nucleophile, and this is going to be our electrophile, at least in the first step. Oh, the other thing you need to know about the Robinson annulation is it's nothing special. It's just one, a Michael reaction, followed by 2, an intramolecular aldol reaction. So, mechanism, nothing new here. It's just going to be long and stringing multiple pieces together. So, first step is a Michael reaction. You're going to use basic conditions, either OH minus or perhaps some organic soluble base like ethoxide. And we're first going to remove the proton from the ketone, the smaller ketone, to give us an enolate. Having done that, our enolate is going to do conjugate addition, Michael addition, to the alpha-beta unsaturated carbonyl compound. This is one step at which you might be asking, why doesn't this ketone simply do the self-aldol reaction? And I'm going to tell you it probably does, and that's where we get this from. But what I'm showing you is I'll address let's just get through the final product, which I guess I should have shown you the final product here. Sorry, kind of all over the place. All right, that's the product of the Robinson annulation. I'm going to show how we get here, and then we're going to address questions of how do I know and what would I do if, and so on. All right, so if we do the Michael reaction, the bond we make is between the alpha carbon of the purple molecule and the beta carbon of the orange molecule. So I'm going to indicate that bond in red. Notice that the beta carbon from my the beta carbon of my alpha beta unsaturated carbonyl compound has 2 methyl groups on it. So there we go. And there should be a negative charge on the alpha carbon, which will be neutralized by picking up a proton from water or from the conjugate acid of my base to give me this 1,5-dicarbonyl compound, the Michael product. Whoops, no, that's right, sorry. Okay. With me so far? Michael reaction? All right. Now, it turns out that the molecule I've made is symmetric. So from this point on, it doesn't matter which side we do the reaction on. For the intramolecular aldol reaction, notice that I made a 6-membered ring, right? I have 2 different kinds of alpha protons that I could remove. I could remove the less substituted one, and if I did that, I would get the more stable 6-membered ring. Or I could remove the more substituted one and get the 1, 2, 3, 4 less stable 4-membered ring. Because this is an equilibrium process, we're going to do what is required to get the more stable 6-membered ring, even though that goes through a less stable intermediate. In an equilibrating process, only the stability of the products matter, not the stability of the intermediates. So we'll remove for the sake of consistency with what's been shown before, what's shown with other molecules in your text, it doesn't matter at all here. It may matter in some other examples, so I want to be consistent with what's done in the text. We're going to remove a proton from the less substituted carbon on the end. That's going to give us the corresponding enolate. Oops. Okay, and then we're going to do the intramolecular aldol. And it can be helpful to number your carbons here. 1, 2, 3, 4, 5, 6. You made a 6-membered ring. Carbon 6 has a methyl group on it and has the negatively charged oxygen from our tetrahedral intermediate. Carbon 1 is attached to carbon 2, which has the ketone. Notice that this is a beta, well, it's the conjugate base of a beta hydroxy carbonyl compound, which is an aldol product. We can protonate the negatively charged oxygen of the tetrahedral intermediate to give us, oh yeah, on carbon 4, don't forget the methyl groups, good. All right, that's close to our final product, but it's not the same thing. It is an aldol product, and you could ask the question, why don't we just stop there? And I don't know, other than it's likely that making this pi bond is favorable because it's conjugated with the pi bond of the ketone. So to go from the beta hydroxy carbonyl compound to the alpha beta unsaturated aldol product, we need to remove a proton adjacent to the alcohol group and alpha to the carbonyl group. That makes our enolate, and this is the E1CB reaction. where we make the enolate first. And then, and only then, do we kick off the OH group to give us our alpha beta unsaturated carbonyl compound. Okay, that's the Robinson annulation. Here's make the enolate, do the Michael, make the other enolate, do the intramolecular aldol, do the E1CB dehydration. To get your final product. All right. So take that in for just a second. What questions do you have? What ifs? Why? What about? Go ahead.
Why does the negative charge on the carbon at the end go towards the oxygen hydroxide instead of the alpha H group instead of the double bond? Double bond is higher than the normal.
Oh, here?
Yeah.
So I think what you are describing is actually another resonance structure of this same molecule. Basically saying, doesn't that enolate have another resonance structure? Yes, it does. That's fine too. We can show the dehydration from that mechanism as well. So you are right. Actually, though we represent the enolate sometimes like this with a negative charge on the alpha carbon, sometimes like this with a negative charge on the carbonyl oxygen, you need to think of it as being delocalized between the two. It's a 3 pi system like we talked about a few lectures ago, where the negative charge is the HOMO of this molecule, and it's delocalized on both the oxygen on the carbon, but a little bit more on the carbon. Yeah, do you have your hand up? Yeah.
Yeah, I was just going to ask what happened in the methyl group, but I think you might have just actually not already because it is in front. So like where the OH.
Yikes. Where did that come from?
So that was just like you have methyl group there, but you're going back to the other things.
Yeah.
Like
The
you
part
had
you just
OH
showed.
and methyl, and then immediately had a.
Oh, yeah. Sorry, we lost one. Yeah. Yeah, you're absolutely right. Sorry about that. Yep, thank you. Yes.
So I know you said you're going to tell us what it is, but how do we stop at the Michael product when we do that? Not the one Robinson.
If you want to stop at the Michael product, how do you do that? Let's actually, to answer that question, let's go back to a previous Michael reaction and sort of say, okay, how do we stop there? One way is to use, let's see. Notice that in the Michael reaction, the thing that does the next cyclization step is the alpha proton from the, what we're going to call the Michael acceptor. Sometimes people call the enolate a Michael donor. And then the electrophile or the alpha beta unsaturated carbonyl compound, they'll call that a Michael acceptor. So in the second step of the Robinson annulation, you make an enolate out of what used to be the Michael acceptor. Challenge up here is, look at our enolate. There's no alpha protons other than the one that was doing, hold on, sorry. By analogy, this is our Michael acceptor, and this is our Michael donor. That would involve maybe this alpha carbon attacking this carbonyl oxygen. So I think because of maybe 1, 2, 3, 4, 5, 6. it's possible that there are sometimes ring strain issues with making a bicyclic system that cause trouble. That doesn't sound like a great explanation for me. The one thing that's likely to happen here is when you want to just do a Michael reaction, you often choose a beta dicarbonyl compound as your Michael donor. And just think about it at this step, once you get to the Michael product. If we were going to go on to do something else, it would need to involve this proton. But that's not the most acidic proton in the molecule, that is. And so I think that's what actually stops you from going on and doing anything else. You choose a beta dicarbonyl compound as your Michael donor, and that itself serves as a deterrent to do anything else, because if a base does anything, it's going to be remove that proton and you're done. That's what I think's going on. And I think your text supports that because most of the examples they have of Michael donors are have alpha protons that would be especially acidic. Even here in this Michael product, there's a reason to expect this proton to be more acidic than these alpha protons once you get there, and that's because you've got this extra benzene ring. So that's actually what I think is going on. That being said, it would seem totally unfair for me to write a question that's like, predict the products of the following reaction. Like, what are you going to do, right? Because there's, well, it could be the hydrate. It could be the enol. It could be the self-aldol. Oh, but wait, it could also be the other self-aldol product. Hold on, we could do a Michael reaction. Nope, that isn't it. You could do a Michael reaction. Oh wait, you could go on to do a Robinson annulation. Hold on just a second, isn't that also an alpha beta unsaturated carbonyl compound? Couldn't I do another Michael reaction? Probably. So that's kind of an unfair question to ask. With the Robinson annulation, it's easier to ask good questions when I say this is a product of the Robinson annulation. What were the starting materials? I could also show you starting materials and product and say which are the mechanistic steps that lead there. In a predict products question, again, if you look at your text, they're going to say, draw the products of each Robinson annulation from the given starting materials. Like I'm quoting from, yeah. All right. Other questions? All right, let's do one, yeah, here we go. Let's do sort of predict the products of a Robinson annulation. So you're looking for a molecule that's going to be your enolate or Michael donor, and you're looking for a molecule that's going to be your alpha beta unsaturated carbonyl compound or Michael acceptor. A hint, in order to be a good, well, never mind. It wasn't that good of a hint, so don't feel bad. Okay, predict the product of a Robinson annulation. First, we got to decide who's our alpha beta unsaturated carbonyl compound. That's pretty okay, pretty straightforward. Second, you got to decide what the Michael donor is going to be. So we need to look at this compound and basically decide of the two alpha carbons, is there a difference in which one is more acidic? Alpha 1, alpha 2? What do you think? Alpha 1, why? Resonance, so it is more substituted, but that doesn't necessarily make it more acidic. That makes the enolate more stable. You've got resonance, it's alpha to 2 pi bonds. If you have a base remove the proton, then the resulting enolate is resonance stabilized in more places. Final exam question. Which of the following carbons shares that negative charge? Do you get why we care about that? That's why that alpha proton is more acidic. It's more resonance stabilized, delocalized in more places. You can go back and convince yourself that the other one is resonance stabilized with the carbonyl oxygen, but not with the benzene ring. All right. So with that in mind, let's do the conjugate addition. I'm not going to, because we've drawn out the mechanism above, I may skip a few of the steps, or I might not. Let's see how we feel. Here is the new bond that we just made between the beta carbon of the orange Michael acceptor and the alpha carbon of the purple Michael donor. So that, and along the way, it can be helpful to just label your carbons to make sure you're doing everything okay. Right here is going to be the alpha carbon. That's going to be bonded to a methyl group and 2 other things, 6-membered ring. On this side, you've got a carbonyl, and on this side, you've got a benzene ring. All right. So then we'll protonate on, and I don't know what the conditions are for this reaction, whether it's water or ethanol, doesn't matter. You use either ethoxide and hydroxide as your base, or water and ethanol as your solvent. Let's see, so that would give us that product. Again, if it helps, you don't have to do this, but if it helps, you can continue to label the portions of your molecule, and you can continue to label what used to be the carbonyl carbon and alpha carbon of your Michael donor versus the carbonyl carbon, alpha carbon, and beta carbon of your Michael acceptor. All right. Now, you've got to do the intramolecular aldol reaction, and you're going to choose the one that gives you a 6-membered ring. Notice that there are no alpha protons here to be removed. Notice that if I remove this proton, I would make a 1, 2, 3, 4, 5, 6-membered ring. If I remove this one, I get a 1, 2, 3, 4, 5, 6-membered ring. There would be a difference in the stability of those 2-membered rings, or those 2 6-membered rings. I don't know whether it's best to try to show both and rationalize why one's better than another, or just to teach you to memorize how to do the right thing. It's probably easier to teach you to memorize to do the right thing. So what you do at this stage is you take the next alpha proton from the Michael acceptor, you remove that proton, and then you do the intramolecular aldol with that. If you want to go down the rabbit hole of thinking about the other possibility, happy to do that. Come talk to me during my office hours and we can look at it.
So you always take it from the one that was previously the
Yes.
Michael,
Yeah. I can't be right, is it? 1, 2, 3, 4, 5, 6. There's likely a clear choice as to why that's the case. I'm just not necessarily wanting to think out loud in front of you guys and may possibly confuse you even more than I'm already confused. So right now, yeah, you take the other alpha proton, attack the carbonyl carbon. Since you know what aldol products look like, I'm going to abbreviate the last couple of steps. If you want to fill in the mechanism later, you certainly can. After that aldol, this would have been a hydroxy group, right? And then we'll do the E1CB elimination to get that product. All right, so that's predicting the product of the Robinson annulation. Yeah, questions? Now we need to get good at thinking backwards, because we're going to start drawing these products and saying what were the starting materials. Yeah.
It would be just as reasonable to have the pi bond in the other ring, right? You could take it from the other hydrogen.
No, the reason why so the precursor is a beta hydroxycarbonyl compound. You are proposing removing that proton. The answer is no. This one is not as acidic as this one. This one's adjacent to a carbonyl. So, and remember, you form the enolate first, and then you kick off the OH group. Finally, in addition to that mechanism issue, the product here is conjugated and therefore more stable. The pi bond here is conjugated to this ketone. Alternatively, what you're proposing is this, and that's a less stable situation. Yeah. All right. So when we take a break, while you guys are doing that, I'm going to play around with the other option and try to see if there's a clear reason why we shouldn't do it. And then we'll start up about 9 o'clock.